Kinetic energy is one form. Do you know what that word means? Moving? Good. You heard of kinesiology? Kind of comes from that word. Kinetic energy, which is moving energy. We'll see why in a sec. And I always abbreviate this. Gravitational potential. I just usually abbreviate. We don't always say the word gravitational because it's kind of understood. Potential. Okay, kinetic energy, they'll say EK, and I believe that's what it'll say in your formulas in the back of your book. Yep. All right, but if I say KE, because that kind of makes more sense to me, and I hope you realize why it does, it's the same thing. Okay, energy, kinetic energy. So potential energy then is energy potential, or PE. Okay, not physical education, potential energy. Gravitational. The other form is thermal, which you guys probably recognize that word. All right, some of you have thermoses today. So we'll get into all that terminology stuff, but first, well, let's just get to it. Kinetic energy. The key word is moving. Anything that moves, we just came off of momentum. If it's moving, it has momentum. The formula was mass times velocity. The mass doesn't really disappear. Okay, if you've got a certain amount of matter, it's still there, but the velocity might be zero, in which case you have momentum of zero. Same thing with kinetic energy. And if you want to know where the formula came from, feel free to look, but I'm just going to tell you that's what it is. It's 1/2 mv squared. It's the square of the velocity. So looking at that, having a little mathematical sense, the mass can't really be zero, but how much kinetic energy do you have if the velocity is zero? Put it in the formula. If that's zero, anything times zero is zero, then your kinetic energy is going to be zero. Okay? If it has kinetic energy, what's our definition of energy? Capacity to do work. If something is moving and it has mass, which there isn't really anything you can describe that doesn't have mass, it can do work on other objects. And this is how machinery works. Okay, we want things to move. They do work for us. Okay, so a couple of quick little examples, just looking at that formula. KE is 1/2 mv squared. A golfer wishes to improve his driving distance, which means his big stick, his 1 wood. Which would have more effect? Explain your answer. Doubling the mass of his golf club, or doubling the speed in which the club hits the ball? Well, this is kind of simplified. I'm not going to get into the details, but just according to that formula, again, what's the relationship between kinetic energy and mass? If the mass is doubled, then mathematically, what's the kinetic energy? It's doubled. That's what we call a proportional relationship. Okay? So doubling the mass, that means the kinetic energy is double. However, V, that's the square of V. So what happens if I double V? What happens to kinetic energy? What is 2 squared? 4 times. Okay, that's not a, it's proportional, but it's to the square of V. It's not a direct relationship between M and kinetic energy. Okay, it's the square of V. Everyone sees that? Right? Just put in a 2, see what happens. So if I double the speed that the club head strikes the ball, then kinetic energy would be quadrupled, times 4, and so on and so on. Play with different numbers. So you could argue this is going to make twice as much difference as that. Okay? Now, like I say, it gets kind of complicated because if you put spin on the ball, of course, it doesn't go as far as if you don't. And there's always people trying to overswing, and bad things happen. Plus, if the mass is increased on your club, it's actually slower you're able to swing this too, right? So it has a double whammy effect. Anyway, you don't hit it as far because usually you put spin on the ball, which makes it go like if you hit it 150 yards that way, but also 80 yards that way, you're probably better off just hitting it 130 yards with no spin, right? So yeah, it went farther, but if you lost the ball, is that really something to be proud of? No. Anyway, I'm an avid golfer, but according to this question, speed's going to be better to try to improve, okay? How much work must be done to accelerate a 100-kilogram motorbike and its 60-kilogram rider? Well, these are joined, aren't they? I would hope so, unless you get in an accident. So let's just call that 170 kilograms. Is that the unit you want mass in? Yeah. Yes. Okay. From 0 to 80 kilometers an hour. Is that the unit you want your velocity in? No. What's that in meters a second? How do you do that quickly? Divide it by 3.6, and that's 22.2 meters a second. So first thing you should do, right? How much work? What are they talking about? How much energy? Do we have a formula that relates mass and velocity for energy? Yes. And today, well, at the moment it's easy because, you know, we're only looking at one formula here, kinetic energy. You got a mass, you got a velocity, put them in this formula, and you know the kinetic energy. Or in the wording of this question, how much work you got to put into this system to do this. Raise this thing from 0 to 22.2 meters a second. Okay, so kinetic energy is 1/2. The mass is 170. The velocity is 22.2. Don't forget to square it. And should be quite a bit, right? So you can go 1 divided by 2 or 0.5. Same thing, right? And what unit is this in? So again, we're not too concerned with sig figs, but don't like give me tenths. But if you are accurate to sig figs, how many do I have here? That only has 2, right? So I'm sure your answer in your book will say 4.2 to how many zeros? 1, 2, 3, 4. Okay? And again, if this is a test and you want to put 42,000, that's fine. If you want to put 41891, that's fine. Okay? So I'm not that concerned. But if I'm in a bad mood, like on your midterm, don't forget units, guys. I was nice. I didn't take off any marks, right? But don't forget the unit. Okay, these next couple, I'll actually get you to do that one. Note that it's in grams. This one will wait till tomorrow because it's a little bit something different. That's kind of all you can do with kinetic energy. This is gravitational potential, or we just say potential energy, implying that it's gravitational. So, if I lift this thing, it has potential energy. It can do work. Think of it as a hammer. How do you hit a nail in a hunk of wood? You lift it up. You probably don't let it go. You probably put some more energy into it and force it down. And if you're really accurate, a lot of guys, if you're in the trade, you can hit a nice long nail on a piece of wood, maybe only hitting it twice. But if you're an amateur, maybe you got to hit that thing 10 times. You're not as efficient, right? But you want to make sure first you don't hit your hand, right? So it takes some practice. But those guys that are really good, they can hit that nail a couple inches away from their thumb, whack, whack, it's in the wood, they're on to the next one, right? So anyway, this thing is gravitational potential. If I drop it, pretending it's a hammer, it could hit this nail into this wood and do work for me. I put work into it, and I let it go, and it gives me work back, okay? So you can think of it as the same amount of work, maybe one's positive and one's negative, or maybe I want to take that as negative, me putting the work into the system. I put in negative 200 joules, and I let it go, hammer hits the nail, and I get 200 joules of work out, okay? But if it's halfway down, it's not zero. Maybe I got half of that potential out. So there's an infinite amount of potential energies from however high it goes to the bottom. Okay? This is the formula. And we have an H in there. Does that kind of make sense? Yeah. How high this thing goes based on our reference level, because everything's compared to something else, right? That's our height. We have mg, which is, what's that? Have you seen that before? Is that a force? A force of weight? Force of gravity? That's weight, right? So that's the weight times the height. And this thing also, it's energy, so that is in joules. Okay, so there's only 3 variables in here. You see the relationship between potential and mass? If this basketball had twice the mass, how much more energy would I have? Twice as much. Directly proportional. If m's doubled, then potential energy is doubled. Height, if I lift it twice as high, then my potential energy is twice as much, okay? Directly proportional linear relationship. So there's not much to do with that question, but we do want to talk about this, because everything, it's always compared to something else. When we get to relativity chapter, you'll really understand what we mean by reference point. Maybe. Is $100,000 a lot of money? It's a relative statement, right? It's a lot of money for a car. Is it a lot of money for a house? I don't even think you can get a house for $100,000 in this province. Maybe a trailer on a tiny little plot of land in the middle of nowhere, provided there's no nice trees on the land or oil underneath it. Right? It's depending on what reference point you're talking about. So, if this is my reference point, does this thing have height? Yes, it does. Okay, but if I got a table here, does that thing have height? It depends. Is the table where I'm talking about where the H is 0? That's my reference point. Or is the floor where I'm taking my reference point where the height is 0? Does this thing have potential if I lift it up? Yes, it does. Okay. Does it have potential now? Well, if this was my hammer and I had a nail down there, I could do this, right? And there's still potential. So it depends. Am I talking the table or the floor? Does it now have potential on the floor? Common sense would say that's kind of like our floor level. But, Colton here gets out his shovel and digs a hole. So now it does have potential, doesn't it? And yeah, we could keep going and going and going. So all I want to make point of is It depends. We can assume in a question if it doesn't say, I'm not here to try to trick you. And I don't want to see an answer like, well, it depends, so I don't have to answer it because they're the, okay? Don't give me one of those. Right? But we just have to be aware of this. Both answers may be correct, but you obviously got to give me an answer. Okay? So there isn't much to do with potential energy. I'll give you these three in a sec. Here's where the real fun comes in. You remember momentum? Okay, a lot of you have found it kind of tricky dealing with conservation of momentum, but as it turns out, most of us were able to understand it because the average on that little quest we did was 81%. So this is very, very similar to that. Energy is conserved in a closed system. This closed system might be Earth. Okay? And it doesn't matter how often the sun keeps shining on Earth. Does it get hotter and hotter, ignoring global warming? Over the last few million years, do we just keep absorbing that sun and it gets warmer and warmer? No. Right? Gets hotter in the day, gets cooler at night, it's cooler in the winter, hotter in the summer. Did I say summer? But over the years, on average, it's pretty consistent, provided you stay in the same spot on the globe, right? So all this energy that the sun gives us, it must balance out somewhere, right? It gets irradiated back to space. But this thing's in balance. Total energy is conserved. We're not looking at something that huge. We're just looking at a tiny little system. But total energy is conserved. So let's go back and look at this basketball. At the top, if I take that as the maximum height, and you can argue, well, it can always go a little bit higher, but for this system, that's the top. All this energy this ball has is gravitational. There's no kinetic, or is there? Have we done problems where something is at the top? What's the velocity? Right. And because kinetic energy is 1/2 mv squared, there's no kinetic energy at the top, right? So all the energy this thing has is all gravitational. When it hits the ground, if I take that as my reference level, the basketball can't get any lower. How much potential does it have? Yeah, because height is 0, potential energy is 0. Exactly halfway, the energy that this ball has is half and half. Okay, energy that this thing has is conserved. Everywhere, and I said there's an infinite number of places this ball could be. Whatever energy this system has, everywhere in here, it's 100% of the energy. Okay, none of it's lost, none of it's gained, it's conserved. So halfway it would be whatever energy it has, I don't know, 100 joules. It's half potential and half kinetic. 3/4 of the way down, okay, it's 1/4 potential, 3/4 kinetic, and so on and so on. We're not going to give you really complicated questions, but maybe 1/4 of the way down, 2/3 of the way down, something like that. We can figure this stuff out. Here's another little example to show us that. So, friction. What's my coefficient of friction here? Nothing, which means he's going to keep doing this forever. There's nothing here to slow him down. Newton's first law says things in motion stay in motion. That's gravity's what's making him go from here to the bottom, right? There's no friction. There's no, what are the forms of friction that this guy would have in real life? Air resistance. What else? The wheels and the track. Okay, yes, and the wheels and the ball bearings in the axle, they try to minimize that as much as possible, but there's still some friction in there. There's lots of different sources of friction here. Do those wheels actually heat up as they roll? Sure, some of that energy is converted into heat. It's also converted into heat from the air resistance. As he's pushing the wind, those molecules are speeding up. They're getting warmer. Okay? So some of this energy is lost. But if we ignore all that, this guy will keep going forever and ever and ever. So, energy is conserved. If none of it's converted to other forms, the potential and kinetic this guy has, it's conserved. So let's look at this. The one on the total right says total. Total energy. Does it change? Whatever energy this guy has, that's how much energy he still has. It's not going down over time. Okay? Even if there was friction, it would stay there. It's just he would slow down, and one of these bars would say thermal, and it would raise up as time went on until he stopped, and all of this energy would be converted into thermal. But I have friction turned off. So the only two sources here are kinetic and potential. You notice what's going on here? The total amount of energy is being converted from kinetic to potential, back to kinetic, back to potential. When's kinetic zero? Right there, right there. What do you mean, no? Right at the top, pretty close. Kinetic is zero. What's his speed at the top? Nothing. So it's all potential. You can see potential is almost 100% of it. Right at the bottom, yeah, pretty good. It's all kinetic. All this energy, there's my zero level right at the ground. There's no potential here. Okay? It's all kinetic. And everywhere in between, there's an infinite number of points where it's some percentage of kinetic and potential. Okay? Make sense? Let's look at one more. According to this, the total energy of this system is 5 joules. And here you can see it's also getting converted from kinetic to potential, back and forth. That's what we call periodic motion. You do that a lot. Those of you taking Math 12 next semester. Okay? Is that a sine wave or a cosine wave? You'll be able to know. But it looks pretty consistent, doesn't it? It's perpetual. Goes on forever and ever. Okay, so that's what we're going to do. Some problems where we convert back and forth and back and forth. The law of conservation of energy. There it is. Okay, it's transformed from one form to another, but it's unchanged. And does this kind of look like momentum? We can have the momentum of that car, and we can have the momentum of that truck before, and then after we got the momentum of the two things. And we can give you this, this, and this, and maybe you figure out the mass of the other vehicle. Maybe we give you that, that, and that, and you figure out the velocity. Okay, there can only be one variable here. Everything else we have to give you. Okay, so that we've already done. So, let's look at this guy. Simple little pendulum. I got one in my pocket. Oh, look. I'm not trying to hypnotize y'all. You will learn physics. But if I had no friction on this, it would keep doing that forever and ever and ever. Why does it look like it's still doing it forever and ever and ever? Because a tiny little bit, yes, it takes years of practice to do this. What is right here at the top, and it's not the top per se, I'm spinning this right around, but however high it goes, what is the kinetic right here? No. Nothing. If I take this as the top level, kinetic is zero. So all the energy this thing has is potential. There's some height here. That's as low as it's going to get, right? Right at the bottom. I know if I drop these keys, I can get work. But as far as this problem goes, that's the bottom. So this height here is going to give me some potential. It's all potential right there. MGH. Right at the bottom, what happens? potential is 0, all the energy is kinetic. Okay, so simple little question. This pendulum bob is pulled back far enough, it's raised that high above its original level. So I start here, there's 0 energy in this system, I give it some potential, I raised it 0.36 meters, and we want to know what is its speed at the bottom. Simple little question. So the whole system, we would go, if I wanted to be really picky, energy before is energy after, just like momentum, before being at the top, okay, and after being at the bottom, which probably makes more sense in this question. This thing has possible potential and possible kinetic. And at the bottom, it also has possible potential and possible kinetic. But what do we know at the top? Kinetic is 0. So I can ignore that, scratch it off. And what do we know at the bottom? The height is 0, therefore the potential is 0 at the bottom. So all I have left is mgh is 1/2 mv squared. This is the top and this is the bottom. Without even looking at numbers, what can I do with my m's here? Yeah, that's why we don't even need to give you the mass. There's no mass here. We don't care. Because divide both sides by m, it's gone. So now I have GH is 1/2 v squared. Do you know G? We're assuming this is on Earth. Do you know H? That's the height. .36 meters. A half's just a half. I can solve this thing for V. So a lot of you guys will put the numbers in now. What the big kid way of doing it would be to make a new formula first, then put the numbers in. Okay, I don't care which way you do it. Just make sure you get the right answer. I want to solve this thing for V. That's what I'm trying to find. What can I do with a half? Divide half both sides, or what's easier? Multiply both sides by 2. Right? Because what's 2 times a half? It's gone. So V squared is 2GH, and V is the square root of 2GH. There's like my little formula for this problem. Put in G, put in H, not 3.6. Okay, take the square root of it, and that'll be my velocity. 2 times 9.8. Jeez. Times. Oh, what is wrong here? 0.36. Okay. 2.66, I guess, is good. Look reasonable? I guess so, right? How fast does the pendulum go? Depends. Seems reasonable. All right. That's conservation of momentum. So 143, number 4. 144, 1 to 3. 147, 1 to 3. And 148, 2 to 6.